right, Master of Science students, let us proceed from where we left last time. We're mostly concerned about thermodynamics. Now we want to look at a new area of kinetics, and this one is going to be slightly more mathematical. But what I'm going to do is that there are some reference books which I'll put on the Google Docs folder to be able to give you the background that you need in the mathematics, all the way from trigonometry, uh, calculus, the differential integral calculus, another concept that you require in mathematics. Especially, you're going to realize that these books uh, do not assume that you require certain knowledge. They just give uh, the basics of mathematics. Uh, in other words, you're saying you can even get even the mathematical concepts of what you may have forgotten, like in primary school. So don't worry about that. Okay. So let's get back to to what you're talking about. Kinetics is the area of chemistry that is concerned about reaction rates. Okay, in talking about, for example, thermodynamics, you can say that the delta G is negative, and therefore um, uh, the reaction is spontaneous. Yeah, but uh, okay, let me say out of here, you may want to set up an industry. Yeah, as a chemist. Yeah. Um, if you're going to be setting up a business and you want it to be really be running, you'll be worrying about, hey, I've got a place uh, where I've probably rented. I, every month, the landlord requires certain amount of money, and the workers need to be paid salary, all those kind of things. There is electricity bills and everything. So, in other words, you'll be looking at am I operating at a loss, or have I broken even? So, in other words, you'll be just be saying, hey, I'm not just concerned about uh, whether I'm getting my product in, whether I'm doing a reaction and I'm getting a product. I've got to see, hey, am I getting this product in the shortest time possible? Am I getting the reaction? Am I getting the product, the useful product, in the shortest time possible? So in other words, you'll be looking at something which you call the reaction rate. This is what I'm going to produce. What is the change in the concentration of the product? I mean, the concentration, change in the concentration of the substance. Let me just use the substance, because in this case, you're going to realize there will be two substances that are going to be of interest to you. One will be uh, the reactant that is being consumed, and then the product that is going to be formed. The rate at which, in this case, I say the rate at which I'm getting the product that you want, or the rate at which the reactant is being consumed. So you're going to get something like if you're going to be plotting a concentration versus time. So you're going to get something like you can get a curve like that one. But once again, let me leave it here, because we're going to be looking at more later on this uh, uh, rates of reaction, in which we'll be looking at zero order, first order, second order. Uh, as of now, I think we'll only be looking at zero order, first order, and second order. But anyway, we're going to really come to that one, and we're going to be seeing that reaction rates, you cannot be able to predict with an equation. You've got to determine them experimentally. You've got to determine them experimentally. So let's come to this, that the rate of the reaction is given by the change in the concentration of the substance, which is given by in the molarity uh, per, uh, per time. In this case, it can be Time can be, if possible, it can be in seconds, if a reaction is fast, or it can be minute, hours, and uh, less likely the reaction, the time will be measured in days, yeah, or weeks or whatever. But usually, the normal units are seconds, minutes, or hours. Yeah. So uh, so the change in the concentration in this case, the concent so the rate in this case is said to be is going to be proportional to the uh, concentration of the reactants. So it means that that uh, 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 if you're going to be removing the, what do you call, the proportionality sign, to say is going to be proportional, then you're going to say there is a that constant which you're going to put uh, next to the one which will be changing. In this case, is the concentration. The concentration, scientists have, or the chemists have come up with just a standard way of saying a concentration is just shown by square brackets. Yeah, that is to distinguish from uh, from normal brackets, which are for a lot of mathematical equations. So when we'll be dealing with concentration, we're going to be focusing on that. Maybe it was not explained at undergraduate, but as of now, when we'll be dealing with concentration, we'll be dealing with square bracket. Now, once again, I hope this thing can be clear here. We are saying that the rate is going to be proportional to the concentration of the reactants. In this case, I just said, what if you've got just one reactant, which I'm going to call A? In this case, I'm going to say the rate of the reaction is going to be proportional to the concentration of the A. So if you're going to remove the proportionality constant, then you're going to get, no, the proportionality sign, you're going to get a rate constant. Uh, Now, this one you're going to be explaining later, uh, this time, and you're going to see it's going to be very important. A lot of things you're going to be, uh, they're going to be dependent on that rate constant. Rate constant is going to be very important. Yeah. Yeah. So if the rate of the reaction is going to be proportional to the concentration of two reagents, which are going to give letter A and letter B, then you're going to say the rate, uh, this mathematical will be shown as rate constant multiplied by the concentration of A and multiplied by the concentration of B. Or if it is if it's going to be, if the rate of the reaction is going to be changing with the uh, in this case, it's going to be doubling uh, of the concentration of A, then if you're just going to open it up, it's just going to be A squared in this case. Now, something which is going to be important, and I need to lay emphasis on this. Now, these are not the stoichiometric balancing of equation. These are these terms A, B, C, and D are determined experimentally. Are determined what? Experimentally. So, uh, so if the in this case, uh, this is an experimentally determined equation. It is not what I'm saying is this. Uh, we can give a chemical reaction that A plus B gives C plus B D. But what you're going to realize experimentally is that A may react with or may react with B to form an intermediate. That intermediate may react with probably some of the A to give another intermediate, and then those ones are going to react to form maybe C, and then C, something like that. You understand? So the normal chemical reaction which are given is the final equation, in which you just say reagent A reacts with reagent B to give C and D. But in reality, you're going to say that um, the reaction may proceed through a lot of intermediates. a lot of intermediates. That one you're going to be looking at those equations. They're going to be a bit mathematical, yeah? But I'll we'll just try to see how we can be able to really understand those equations. So if uh, if if we just know that these are the moles of A of the reagent A and these are the moles of the reagent B are going to give reagent C and this one reagent D, then the rate can be expressed as the following. Let us see what is happening to the starting materials. That is A and B. Can you see from this equation? Yes, this graph here. A, if these are the reactants, they are decreasing. So you're going to say, and the rate will be said to be the final minus the initial. So in this case, for example, A, maybe the final concentration will be maybe something like 20 moles, and maybe you started with 50 moles. So the change in the A will be 20 minus 50, so it will be minus 30, negative 30, yeah? So, so for the reactants, you're going to have a negative sign. It means that reagent is being consumed, yeah? So there will be, and once again, I'll be referring you to that book which I'm going to be explaining on the WhatsApp on how to get the link. Uh, so in this case, this is the rate of change, yeah? Delta means change in the concentration of A over time. So I'm going to put a negative. It means that the final concentration of A minus the initial one is going to be A. The final will be less than the initial. So I'm going to put a negative sign. And the same thing about if I'm dealing with reagent B, it will also be consumed over time. Yeah. Now, what is happening to the products? Initially, there was zero. And then after some time, the concentration of the product will be starting to increase. So the final concentration of the product is going to be larger than the initial one. So the change in the concentration of the products, like in this case C and D over time, is going to be positive. Yeah. So just remember this equation here, that if you've determined experimentally that there will be moles of A is the moles of A, B for B, C, and D, then that is how you're going to know the rate of the reaction. Yeah, 1 over A multiplied by the rate of change of A and minus 1 over A times the rate of change of A over T is equals to negative 1 over B. Uh, and which will be equivalent to 1 over C, 1 over D, something like that, yeah? So that equation, I believe it can be seen quite well, okay? And once again, I'm just revisiting this because there's some terminologies that I want to bring in, and we'll come back to these rates later, yeah? We're going to be looking at those things about zero order, first order, second order, and how to determine those rates if you're given experimental data. Yeah, yeah. So you are a chemist and you need to know how to be able to see how you can be able to determine the rate of a reaction uh, experimentally. Now, let's get back to the reaction coordinate diagram which we learned earlier. In this case, that's like the free energy. This is the progress of a reaction. Yeah, it can be seen quite well. R is just the reactants. This is the product, and in this case, um, uh, there is the free energy of activation, or it can be in another case it can be there can be uh, uh, so there is the uh, free energy of activation, and then there is the activation energy. These are two terminologies that are mentioned interchangeably, but I need to tell you that they are quite different. Delta G of activation is given by delta H of activation minus the absolute temperature multiplied by the entropy of activation. Just as the same as the delta G naught is equal to delta H naught minus T delta S naught. Yeah. So for activation, you're going to be looking at the reaction under those conditions. Now, what has been seen is that the activation energy is given by the delta G plus plus RT. Yeah. Yeah. and and then there's another equation which you want to introduce, which are going to get more information about it in the physical chemistry. As I mentioned, this is organic chemistry, and in organic chemistry, we try to avoid duplicating what you're supposed to be learning in physical chemistry. So if the derivation is supposed to be coming in the physical chemistry, then I'll try to say, wait, if not learned about it, wait until the lecturer who is teaching in the physical chemistry is going to do that one. But there is this free energy is given by uh, gas constant RT, and then there is the uh, log base E of the equilibrium constant. And once again, as I mentioned, um, uh, maybe later I'll be able to tell you how do you, what is this thing you're going to call natural log, yeah? I'll be able to guide you. I want to see whether I can be able to guide you to the relevant page in those books which give elemental mathematics, which you require to be able to understand this course in SCH 503. But delta G is given by this equation minus RT log base E, or natural log of the equilibrium constant. And the equilibrium constant uh, can be determined by the concentration of the products over the concentration of the reactants, isn't it? Are we to get on that? Yeah. So given that you've got your delta G here, which is given by this equation, and also delta G is given by delta H minus T delta S. So you can be able to just say this expression here, I put it on the left, and it's going to be equivalent to this other expression because they're referring to the same variable delta G. Then you're going to get minus RT ln K is equal to delta H over minus T delta S. So if you're now going to rearrange to form to make the uh, equilibrium constant as the what, as the main subject, then you're going to get minus delta H over RT plus entropy over R. What does this tell you? You can be able to determine from titration and other methods uh, how the concentrations of uh, the products that you're going to be getting. If you're talking about, like in this case, like what, a reaction like which one? Like the hydrolysis of the carboxylic acid. No, the hydrolysis of the ester. In this case, you've got your ester plus water, and it's forming carboxylic acid plus alcohol. So you can be able to determine uh, uh, concentration of the acid that you are, carboxylic acid that you are forming uh, by reacting with what, something like maybe doing a titration on what, uh, like with sodium hydroxide and with phenolphthalein, you'll be able to determine the concentration of the carboxylic acid. And now, given that you know the concentration of the acid will be the same as the concentration of the alcohol, that would be easy. And then you'd have known how much of the ester that you put initially. So in that case, you can know the number of more. I mean, from the weight will be the what? Weight will be uh, relative molecular mass times the moles. Yeah, you'll be able. So in that case, you can determine the concentration of the reactants and the products. So what does that tell you? Looking at this equation, which are going to be called the Ehring Eyring equation, Eyring, what can you say? These are variable equilibrium constant which you can determine experimentally. Uh, Enthalpy of activation are usually known if you're talking about certain products that you're forming, you can be able to find those enthalpies from the tables. R is known. You're doing a reaction at a certain temperature. If it's 25, then the T will be 298. And then once again, this is the gas constant. So in this case, what can it tell you? You can be able to determine the entropy of a reaction, whether the entropy is increasing or decreasing based on this equation here. Can you see that? Yeah, it's called the Eyring equation. So we are going to be looking at, in a short while, a certain very important equation. It's going to be related to the rate constant and and somebody who was plotting the rate constant for certain reactions versus temperature, and then it trying to get certain uh, uh, and then it got a certain relationship which I'm going to call which I'm going to see later. It's called the uh, Arrhenius equation, or Arrhenius law, as it's called. You're going to see it is one of the most important equations in what I call physical chemistry. So you're going to come to that one, and it's going to be related to the activation energy. How, if you know the rate constant, which you can determine experimentally, knowing whether you're dealing with first order, second order, and zero order. So that in this case, you've got your concentrations, and then you've got your time, and then get the rate constant. Uh, what you're going to see is that you can be able to determine the activation energy of that reaction. And activation tells you, hey, this is the barrier that I need to overcome to be able to do this reaction. So keep note of this. This is the rate constant, which you can determine experimentally. I've talked of the activation energy, which is given by delta G plus R. You're going to see how you can be able to determine the activation energy experimentally. Can you see these equations? You're going to be relating this rate constant with this activation energy, so that you're going to see some of these things are not just theoretical. You can be able to determine them experimentally. Yeah, you can be able to determine what those variables experimentally. So you're going to stop there, and then the next thing we'll be looking at the Arrhenius equation, and then we'll see how you can be able to determine the activation energy experimentally from the rate constant and the reaction at whatever temperature that you're carrying out. Okay. I hope you've really enjoyed uh, this session on the kinetics. It will be a bit mathematical, but once again, mathematical which will be able to, which is not very complicated. It will be mathematics which you may have dealt with, but as I mentioned, there are those books that are going to be giving you the background that you need to be able to understand the concept that you're talking about. So we'll stop there, and then we'll proceed shortly. Yeah. Okay.